Recording. Man, I don't know why V keeps skipping this class.
Because I don't like you.
Totally recorded. All right. So as many of you know, the new CS major starts in the fall. Now, while this doesn't directly impact most of you because you're too far into the program to legitimately switch, although if some of you can make something line up, then it would be possible. If you've taken enough of the classes where it does work, you can get the, you can switch this catalog year and get the right, or the concentration designation on your transcript. But in any case, I wanted to point out a couple of classes from, let me switch this. Let's see.
Who is 460 taught with?
I think Dr. Wall. I'm bringing up the fall schedule here.
All right.
And we'll talk about what might be good replacement classes for some things. Okay, so this is the fall schedule for this coming fall, which is actually a slightly different schedule than there will be for typical, the typical schedule. Hold on, let me get the chat thing open. Oh, that's fine. All right, so, and the reason why the fall schedule this fall is going to be a little different than the fall schedule in the future is we've had to make some accommodations for the current 200 students that are, they took 200 this spring when 200 is now going to be a fall course. So we had to add a couple of like 250s next semester when in the future it's going to actually be in the spring. But in any case, so classes that would be good to take next semester, I want to highlight a couple of the interesting new classes. One is CSC450. This is part of the new cybersecurity concentration. So this class is called penetration testing. So it's ethical hacking or like a white hat hacking. So the idea is that this is kind of the applied side of cybersecurity, where you look at current industry tools for stress testing computer networks and computing systems. So the idea is that if you're somebody who's in charge of making a computer system secure, you have to pretend to be a hacker. In order to pretend to be a hacker, you need to know how the hackers think and what tools they use and try to break into your own system. And that's what penetration testing, that class, is about. The prerequisite for that class is 200. So any of you, you don't have to take 426 before you have this class. I know several of you already have 426, but this would be a reasonable class to take in the fall. I know a couple people who are trying to graduate in December were expecting to have 490 here in the fall. We're not offering 490 in the fall because now we flip-flop 491 and 490. So 490 is actually a spring class, so you do your senior project in the fall semester. So because of that, if you need 490 and you're trying to graduate in December, we're going to let you replace 490 with either 428 or with 417. No, 419. Where's that? This guy. This is the new machine learning and robotics course. So the prerequisite for this is, I think, tactically CSC 200. Maybe it should be 250, but whatever, some programming class. But you don't need to have had 415 before you have this one. So this isn't an intro to AI, it's an intro to machine learning specifically. where there's a 417 class now, which is AI2. You do need 415 before you can take 417, and that's offered in the spring. So classes that I would highlight for this coming semester for those of you who are still going to be around are CSC428, penetration testing, and 419, machine learning and robotics. I think both of those will be pretty good classes. Other things that I would highlight would be the idea of getting an early start on the master's program starting in the fall. It's an all online program, even though we do have face-to-face grad classes that you technically could take if you wanted a face-to-face class. Those exist mostly for the international students who have to have an on-campus presence. So we have 9 credits per semester of the face-to-face grad classes, but those same classes exist in 100% online format. So if you are looking at getting an early start on a master's program, you don't have to worry about the class time because it is all online. And they're in 8-week formats, those classes. So again, encouraged to get a jump start on the master's program. I know Blaine is going to Acuity, and so, you know, might as well do the master's program because Acuity pays for it. So is the punchline. So if you are graduating and going to work for an employer and your employer pays for it, hey, that's free money, not just for the degree, but that's going to increase your earning potential with that employer and other employers quite a bit. But I think that's all I really want to say to this particular audience, is I just wanted to highlight the 428 and the 419 classes, and then an early start for the master's program, which you can do in your senior year, if that was of interest to you. So any questions about any of that stuff before we move on to file system stuff? Okay. Out of curiosity, how many of you are planning on taking either 428 or 419 next semester? Who's going to take 428? Start with that. 0 people taking 428 penetration testing. What about 419? Oh, V is taking, is that thumbs up 428 or 419?
419.
419, okay. So in any case, heavily pushing that. Is Fran not actually here? I think Fran's taking one of those. I think he just logs in and leaves.
Yeah. You might be taking 429 or 428, I assume.
Yeah. Okay. But in any case, I think those will be good classes the first time they've been offered. And the 428 is Dr. Wall, 419 is Professor Locklear, and they're both been actively reviewing textbooks and stuff for them. So I have a feeling they're going to be at least entertaining classes. It is the first time they're teaching it, so we'll see how that goes. But I would think that they should be fairly fun and interesting classes. All right, so let me get this guy. Okay, yeah, so we talked about file some stuff last time. Let me just double check something here real quick. Okay, that's fine. All right, so last time we talked about kind of introduction to file systems, the idea of FAT12, FAT16, blah, blah, blah. Some of those limitations on the file size. We talked about partitions at the high level. We're going to talk about that a lot more detail today. And just the idea of what is a file. So if you think of a file as like a data structure, it holds a collection of bits, but these bits need to be stored somewhere. So on a hard drive, specifically divided up into a bunch of something, you know, I usually refer to as clusters on the hard drive. So what we're going to do is we're going to start off talking about this idea of a cluster. So notice I put clusters in double quotes here because it's kind of a catch-all term, and we're going to separate that into two terms today. So I've said a cluster is kind of a bucket of memory on the hard drive, and it has a fixed size dictated by the file system. So let me introduce a couple of topics here. So first of all, we have something called a sector. So sectors are typically 512 bytes and are designated buckets on a physical hard drive. Okay, so this idea of a sector is not controlled by the OS. This is like a hardware standard. Okay, there are some other other sector sizes for disks like CD-ROMs and DVD-ROMs and things like that that have been played around with, but let's just for our, generally it's 512 bytes for a sector size. So if you think about a hard drive, especially the mechanical hard drives, these guys have a geometry. If you remember when we look at our, let me connect this back real quick to our box. I'm just going to start up Ubuntu real quick. I'm going to show you the box resource file so we can make a connection to that because he's faking a hard drive. All right. Oh, we didn't put a hard drive on here yet. Okay, this doesn't really help me show something. When we put a hard drive into box, we're gonna have to describe the geometry of the hard drive in terms of its sectors and cylinders and things like this. That's where this idea of a sector being a standard 512 bytes comes into play. So almost think about it as like a standard for an array. So we're going to say, think about this as a standard for an array that governs physical hard drives. All right, so if I have a 1 gigabyte hard drive, in order to get a gigabyte, I need more sectors. Okay, and each sector can hold 512 bytes. So if I have 1,024 gigabytes, that's times 1,024 megabyte. I'm sorry, 1 gigabyte is 1,024 megabytes times 1,024 kilobytes times 1,024 bytes times 8 is bits divided by 512. So for a 1 gigabyte hard drive, I need 16,777,216 sectors. That's how many sectors I need if each sector is 512. Oh, I did it in bits. So it's actually this divided by 512. So I need 2 million sectors. And those sectors are divided among, hard drives are actually, we're still talking about the mechanical hard drives. They have a platter that is a bunch of magnetic disks stacked up. And those disks have so many sectors on them. So the more sectors you need, the more things you have to have in the platter. So the more moving parts that you're going to have and that kind of stuff. So the important thing we want to get out of this discussion related to sectors is this is not something controlled by the operating system. Instead, a sector is something that's controlled by the it's something that's controlled by the hardware itself, and it's a standard within the industry. Why don't you just speak up, V, and yell?
I have a question. So you were just talking about the cluster, and then you introduced sector. So how is those two related?
Yeah, I'm getting there.
Oh, I'm sorry.
Yep. So, but here, let me say it this way. This idea of a cluster is my term. I call these guys clusters. It's not just me. It's a kind of an industry term. You'll hear them refer to hard drive clusters. But the idea of a cluster is kind of this hodgepodgey language between what is the standard for hardware versus, and I think this will get to the point of the other part of your question. Let me get to this second slide here called a block. So a block is governed by the OS and is a collection of one or more sectors. So we can think of a block as a data structure for holding data on a hard drive that represents a collection of, we'll say, at least one sector. So depending on the operating system might say, you know what, a 512 byte sector is kind of tiny. I want to have my granularity of what I can store in my hard drive to be bigger than that. I want to be able to hold a kilobyte, or I want to be able to hold 4K, or I want to be able to hold a megabyte, whatever it is. So the OS might say, I want my block size to be 4K. So if I have a 4K or kilobyte block size, this guy encapsulates, so if we take 1020, let's see, 512 bytes, that's a half a K, right? So this is 8 sectors. So 512 bytes is 1/2 of a kilobyte. So 1024 is one, number of bytes in a kilobyte is 1024, divided by 512 is 2. So if I can fit 2 sectors in 1 kilobyte and I want 8, or I want 4 kilobyte block sizes, I will need 8 sectors will be stored inside a single block. A block is an abstraction that OSs use to work with hard drives. And this kind of gets back to that same idea as before, where, understand that the idea of a physical hard drive has been around for a long time, right? So if we go back to a 32 kilobyte hard drive, which we look at today as being useless, but they existed. There was a physical hard drive that was 32 kilobytes in size. And that guy was made up of sectors. Similarly, today, if you go out and get a 2 terabyte hard drive, that guy is made up of sectors. All right. So with that in mind, the idea of a sector has stayed consistent across those hard drives because it's a way of describing the number of buckets in a hard drive. Now, if we connect this back to what we've been talking about recently with memory, the idea is that the more buckets you have, the higher you have to count, right? And if you have 2 terabytes of buckets, with each one being a half a K, for example. So if we just use this as our extreme, we'll put it on a slide. We'll call this the extreme. A 2 terabyte hard drive, which is, let's just get this to bytes. So that's 1024 gigabytes times 1024 megabytes times 1024 kilobytes times 1024 bytes divided by 512 is 2.1 billion sectors, right? What does this number look like to you? Does that look familiar? What's that number? Just say
Is
something.
that the maximum value of 2 to the 32 signed?
Which is what?
The max we can hold in a
What's the data type?
32-bit.
It's an int, right?
Yeah.
It's an int. Okay, so this is the biggest integer, meaning that if I go over 2 terabytes, I can no longer count to that with a 32-bit integer. I have to use now a 64-bit long to count higher. You see our limitation? So the idea here is that if we're going to keep our, now we might also say that with 512 bytes, almost everything is going to be bigger than 512 bytes by today's storage standards. So for an OS, they might say, you know what, I want to be able to have bigger hard drives than this. So shouldn't I be able to stuff more sectors into a single block to give myself, I mean, I know I'm going to have to store this file in a minimum of, let's just assume that we say that on average, the minimum file size is 4K, right? That means we need 8 sectors to represent 4K. So we might say that on our file system, we're going to have a single block being a cluster of a cluster of 8 sectors. So 2 terabytes, let me just finish this slide here. 2 terabytes is this many this many 500 and, well, let's say, just say sectors.
I have a question.
Go ahead.
So aren't you supposed to times that number by 2 because you just take 1024 and you do a whole bunch of conversion, but this is 2 terabytes though. That's just one. No?
I need to actually have it by 2, right? So this gets me.
No, what she was saying was that you were counting up how many bytes in a single terabyte and then dividing by 512.
Oh, yeah. Thank you. So times 2 is going to be 2 terabytes divided by 512 would get me size. This is actually size of unsigned 32-bit number. So we went down the same path as just being unsigned 32-bit int. All right, so, but we'll correct that value. A lot of sectors. So 2 terabytes equals a lot of sectors. But we would say that will we ever really have a file that is only 512 bytes big? Or will we usually have larger files? I think most
days you have to really try to get something as small as 512 bytes.
By today's standards, right? Yeah, we go back to those days where we had a 32 kilobyte hard drive, 512 byte files were probably somewhat common, right? But by today's standards, our average operating systems, as we saw last time, use 4 kilobyte blocks. So 4 kilobyte blocks, we're basically saying, so let's say if modern OS uses a 4 kilobyte block, we are basically saying that we believe that the smallest practical file size will be 4 kilobytes. We can store smaller. We just won't use the entire block and have internal fragmentation. All right, so by a modern example, a 4 kilobyte block dictates that we have, that it governs, it's a data structure that holds a collection of 8 sectors, because the idea of a sector has not changed on the hard drive. So I would say that a block is a cluster of sectors. All right, So let's call these some of our primitive types here. And if we were to draw a picture, and that's what I was getting ready to do at the end of last class, is we have this idea of a hard drive. So this is our hard drive, and our hard drive is organized in terms of 512 byte sectors. All right, he's organized in terms of 512 byte sectors, but then on top of that hard drive, we overlay a file system. And the file system is one of the components of our operating system. All right, so it's one of the things that an operating system does for us. And we might say that a modern operating system abstracts these sectors into blocks of, well, let's call it 4K blocks. Four kilobyte blocks, and I'll put in parentheses 8 sectors. So this block is a abstraction for one or more of these sectors. Modern OSs typically will use 4K or 4096 byte blocks. Therefore, they will have 8 sectors inside of an individual block to hold the data associated with that bucket of a in your file system. So by definition, this guy would be contiguous. A single block is a collection of contiguous sectors. Sectors are contiguous in that it's bucket 0, bucket 1, bucket 2 in 512 byte steps. So they're contiguous anyways, but our abstraction also relies on it being contiguous. So this is effectively an array of these guys, where these guys can each hold 512 bytes of data, of stuff. Where 512 bytes times 8 is 4096 bits. That's the number of bits in a byte is 8. So a single sector can hold that many zeros and ones. Go ahead.
On the kind of low end of things, whether we're running an operating system or any other kind of bare metal program, how does that ask the hard drive for data? Does it send out an address like when we ask the RAM for data, or what are we doing there?
Yeah, so at this point, we've just described what the file system is. You're asking, how do we interact with the file system? So that's what we're going to start talking about, the file allocation table. I think did I give a link to it or open it up last time and say we had I gave you like a Wikipedia because we were talking about FAT8, FAT12.
Yeah, FAT.
Yeah. So I think I have a link open here, but I'm going to actually show a video that I found that I thought was pretty interesting. So I'm going to show that as a quick starting point. It's only like a couple minutes long, but it effectively gives a quick overview of the file allocation table. And then we'll talk about how that fits into what's here. So what I wanted to introduce here is this is our building blocks of a modern hard drive, right? So we take a physical hard drive that is divided up into sectors. Those are little pockets where you can stuff things, all right? Operating system has no control over that. It gets handed a hard drive, and this hard drive has sectors on it. And you can store 512 bytes per sector. That's the rules. You figure out how you want to organize your crap. That's what you can do on the hard drive. All right, then we're going to say we're going to overlay some file system. And we'll talk more about file systems here in a little bit, but some file system. This guy is governed by the operating system. He's one of the subsystems of our operating system that, you know, allows us to interface with this piece of hardware. Now, Appel is asking, okay, well, how does that actually occur? Well, the starting point is that this file system creates a data structure called a block. And this block abstracts sectors into collections of sectors. So a modern example would be a single block on a modern file system might have 8 sectors inside of it to represent a 4 kilobyte block size. So up here, we might say 512 is smallest storage size possible, let's call it physically possible. We're down here, no, this is 512 byte. Down here, 4 kilobyte is smallest storage size allowed by OS. This is a constraint. This is a choice. The OS designer chose to say, you got to store stuff in terms of blocks. The smallest block size is 4K. Anything you try to store smaller than 4K will be wasteful. That make sense? So these are our primitives that we're dealing with here. All right, so let me switch over. Actually, I think there's a thing called optimize screen sharing for video clip. And let me go over to my, I'm lost. And we'll play Airwolf again. Totally should. All right, so here's our file allocation table. You can see the screen now.
The file allocation table format was originally used in the late 1970s on floppy disks and became the standard in DOS and early Windows machines. It is still commonly used on solid-state and flash memory devices like this one. As these storage technologies have evolved, it has gone through many iterations, but the 2 key ideas have remained the same. The first is that each file is represented as a linked list of blocks. Normally, when we think of a linked list, we think of the links as being part of the nodes in the list. Maybe the last part of the block would give the ID of the next block. Here, however, the links in this list are represented in the file allocation table, which is indexed by block.
I'm going to pause this real quick. If we look at these blocks here, we're representing a linked list. Do linked lists exist in contiguous memory? Or does linked list specifically go around contiguous memory?
Go around contiguous.
Yep. So these links that he described here, when he says this block is linked to this block, is linked to this block, and we've said a block is like a 4 kilobyte collection of sectors, cluster. That means that if we have, in his little example here, some file divided up into these 4 blocks, with maybe the last block not completely being filled up, right? But we have this file filled into, split into 4 blocks. These guys do not have to live next to each other on the hard drive. We just have to know where it starts. Make sense? That's what we're trying to figure out, is where does this start? Where is the base address of this block? And then how do I travel from block to block to block to get to the parts of my file where stuff live?
Block number. Giving the starting block number of a file, I can find the next block with a constant time access to the file allocation table. A special value, -1 in this example, indicates that a block is the last in the chain. This file allocation table also contains a bit to say whether a block is free or not. In this example, our file starts with block 2. Looking at the table, I see that the next block is 6. Looking at 6 in the table, I see that the next block is 3. Again, going back to the table, I see that the next block is 5. And when I look at 5 in the table,
what is this file allocation table holding? So notice over here on the left, he has a linked list. So this is how the things are physically stored on the hard drive, right? But what is this file allocation table itself keeping track of? On the left, it's keeping track of whether or not a particular block is currently being busy, right? Because a block might have data written to it. That means that block might be being changed by somebody. So we don't want two people to be able to change a block at the same time, right? We don't want to let two programs change a block at the same time. So they have to wait their turn in order to be able to change that block. So that first bit lets us know whether it's busy or not. But the next bit, this guy says, where is the next node of this block? What do you think -1 means?
Behind it.
The tail.
Right, yeah.
It was
It
the
means
end.
it's the end of the list. Yep, -1
Yeah.
means there is no next block. I'm it. End of the road. Okay, so this file allocation table is a lookup table where if I know the base block, so if I know I'm in block 2, right here, block 2 says his next block is block 6. So where can I find block 6? Well, is block 6 available? Yes, it is. So here's block 6. His next block is block 3. Here's block 3. Block 3's next block is block 5. Here's block 5. Block 5's next block is -1. We're at the end of the list. Our file has now been fully described to us, where all of his pieces, all the 4 chunks of my file live here. This is the actual representation on our hard drive in terms of blocks linked to other blocks. This is what lives in a table in a specific place on our hard drive that we'll talk about, master boot record and GUID tables. But this is a table that keeps track of blocks and their relative location to other blocks. Because when we write data structures, we think about this guy as being a node object, right? And we can ask this guy, where is your next node? Correct? But if this is a physical idea on a hard drive, this is like this template overlaying a hard drive, I can't go to block 2 and say, who comes next? Because I don't have some next pointer on this guy. He's an idea. He's not an actual instantiated node object. We're representing it as a node, representing it as a linked list to kind of indicate these guys don't have to live next to each other. But if we think about this whole thing as an array, the contiguous collection of blocks in our hard drive, we'll have block 0, block 1, block 2, block 3, block 4, block 5, block 6. Those would be next to each other because these guys wrap around contiguous sectors. All right, so I'm not walking. So we talked about being able to look stuff up in the file allocation table to find out where the next block is. So if I'm currently at block 2 and I want to know what comes next, I'm in the middle of reading a file. So we have this idea called blocking and unblocking. So blocking is, I know we'll put it on a slide here in a few minutes, but blocking is the idea of taking a file and splitting it into chunks, splitting it into blocks. Unblocking means turning it back into a file when you need to read from it, okay? So if I have my file spread across these 4 blocks and I want to put it back together, I use the file allocation table to tell me where to go, what blocks do I need to go to, and concatenate the stuff found in those blocks to give myself my original data. And these blocks might not be next to each other in memory, because we would say that, okay, well, now all of a sudden you might have enough total hard drive space available, but you don't have enough space in a row to store something. Well, this guy would guarantee that you get to work with your hard drive that if you need 4K, there will always be 4K available unless you completely used all your blocks. All right. So we visually depicted this as a linked list, but we don't have object access to this guy. If I go to block number 2, what I'm actually dealing with is sector 1024 to whatever that is plus 512. You know, actually, whatever that is, I'm doing math wrong here. I would go to, so the first guy is 8 sectors, all right? So block 0 would be 8 times 512, which gives me sector 4095 as the last sector of block 0. So plus 4096. So 8191 is the last block, last sector of block 1. So the first sector of block 2 would be 8192. That's the sector that this guy starts from, and it's 8192 plus 4096, which would be 12,287. So block 2 wraps around sectors 8192 to 12,287. Those are the sectors that live inside of this particular bucket. Called the bits. Those are the bits that are governed by the sectors. So this covers bit 8092 to bit 12,288 on that, or 287 on that hard drive. And then block 3 would be bit 12,288 to bit plus 4096, 16,383. Block 4 would be 16-bit 16,384 to the next 4096 bits. 4096 bits being 8 sectors. 8 times 512. Where a sector is 512 bytes. Actually, all those things I just said bits are actually bytes. So you actually, that exact example there kind of indicates that why we need these abstractions. While computers deal with things in terms of bits, zeros and ones, those aren't practical storage things for us, right? A bit is too small. You can't store any real data, or you commonly can't store real data inside of a bit. We might say, oh, we need at least a byte. Well, if we're storing actual file system data, what the sectors say is you actually need 512 bytes to really store something meaningful. But by modern day operating systems perspective, we're saying, yeah, 512 bytes isn't going to cut it either. You need at least 4 kilobytes to store something meaningful. So these are abstractions of each other. We'd rather talk about it in terms of 4K chunks rather than bit to bit to bit to bit to bit. All right, so let's let this guy finish here. But you know, that's the idea that I want to point out here. He's depicting this as a linked list to indicate that it is not, that a block 2 is not necessarily, block 6 for this file does not necessarily live in contiguous memory, or let's call it the second block. If this is the first block of this file, this is the second block of this file. The second block is not necessarily right next to the first block in contiguous memory. He's at some block on the hard drive that our file allocation table helps us look up, given the block that block 2 links to. So we have effectively implemented a functional linked list in terms of this idea of blocks and this file allocation table, which tells us where the next block is given a current block. All right, so let's just let this guy finish cooking and then we'll look at some examples.
I see that its next has the special value indicating that we've reached the end of the file. It's important to realize that the file allocation table, or FAT for short, stores all the links for all the files. For instance, there appears to be another file occupying block 4, and only block 4, since that's the end, and also one occupying block 1. So the file allocation table tells us how to glue the blocks of a file together, but it doesn't tell us where to start these chains of blocks. That is the function of the directory tables. Directories, I should say, are indeed treated as files, and they use something called a directory table format. Entries in the table all have the same width and contain the essential information, including the file name, the starting block, and any other metadata associated with the file, such as permissions. The root file directory has a fixed address on the disk, so we always know how to get started. Let's say that I wanted the content of a file /foo/file.txt. I would first consult this root directory table. It would tell me that there is indeed a directory named foo and give me the starting block of that file. I would then access that file on the disk. And
so now if we look at that file foo, and it says the starting block for foo is 1. We look at our file allocation table, we go to block 1, and we see that the actual contents of that entire thing is stored inside that single block. Okay, he's told us that happens to be this file system represents directories within a single block because it's actually just the name of a directory. All right, then he's showing us inside of this directory. So this file allocation table has a file named foo, which is actually a directory whose starting block is at 1. So I go to my file allocation table. Well, I read in block 1, and then I say, well, does block 1 link to anything else? No, it doesn't. He's the end of the road. That's all the data I need to read in. He is a directory. So then I'm in that directory, and I see my directory table. When I do ls or something like that, it's going to show me a listing of my directory. And inside there, I see a file called file.txt. And file.txt has associated with it a starting block. This is the head of that linked list. That's at 2. So that's where this guy is. So in order to reconstruct, in order to unblock file.txt, since we know it's stored in the format of blocks on the hard drive, in order to unblock it and load it into memory, system memory, because ultimately that's where we're trying to put this stuff. When we want to work with a file, we have to read it off of disk and put it into system memory. It's stored in block format on a disk. We need to unblock it and then store it in what format in modern day memory? How does system memory typically store stuff? We mentioned it last class. What's a modern approach to system memory? You're muted, Blaine.
Just like we would think of arrays normally.
Yeah, but
Contiguous.
It is contiguous, but there's a specific memory management algorithm that's pretty popular today. Uses frames and
pages.
Pages, yep. So paging memory management. We need to. This file is stored on our hard drive in block format. We have to unblock it, then divide it into pages and load it into system memory. You see how this is all just moving from one storage medium to another and storing it in the format that storage medium that makes sense for that storage medium? Okay, so file.txt, because we know we are representing this, or this is in a file system, okay, that's governed by this file allocation table. And this directory table, it tells us that, oh, here's a file called file.txt, and the head of that fictitious linked list is block 2. So I go to bucket 2 of my block. I go to the third physical block on my hard drive, all right? Which will be at, so if I'm giving you real values here, so this is the third block times, there's 8 sectors per block. So I actually need to go to sector 24. So my third block begins at sector 24 on my hard drive, because each of my blocks stores 8 sectors. Okay, so this tells us where do we need to physically go on our hard drive, the memory address, so to speak. Where do I physically need to go on my hard drive in order to get to this block? And then I consult my file allocation table, which completes the information for me, because that sector is not going to have a pointer to a next node. The file allocation table is what actually holds that pointer. So block 2 points to block 6. Block 6 points to block 3. Block 3 points to block 5. Block 5 points to null, the end of that file. So I can concatenate all of the bytes that I found in those 4 different blocks together, giving me my entire data for this particular file. So now I have unblocked the file. And now I'm prepared to chop it up into pages and load it into system memory. Go ahead, Blaine.
I think I might have missed this. So sectors are already defined on the hard drive, but are blocks already defined by the hardware, or is that something we have to do with the OS?
OS, yeah. So if I, here, let's just finish the last couple seconds of this, and then we'll go back to it. But blocks are an OS thing. Sectors are a hardware thing.
And since it's a directory, I would look through there for the file name .txt, and it would tell me that the starting block is 2. I can then chain together the blocks on disk, as we did earlier, using the file allocation table. To summarize then, the FAT, or file allocation table, serves as the glue that chains the blocks of a file together. The directory files capture the hierarchy and the starting blocks for the files, and all the metadata.
So,
Question: does the file table, file directory table, and the FAT table, do those take up the same block, or are they?
they're actually stored in something called a master boot record, or more modernly, there's a GUID table. We'll talk about that in a little bit. For right now, just think of them as being stored somewhere.
Gotcha.
If you notice that the first block actually started at block 1, so block 0 is kind of like this, maybe some stuff is stored in block 0. That's kind of where it's going with that. Okay, yeah, so Blaine, that was this picture right here, is that the sectors are part of the hardware. The blocks are part of the operating system's decision. A little bit ago, I said, this is a constraint of the hardware. This is a choice of the operating system designer. All right, so blocks are a data structure that belongs on the software side of things. And a common example for a block size would be 4K by today's standards, whatever. But unless you're dealing with kind of a weird, freaky deaky hardware, that whole idea of a 512 byte sector is pretty much standard for hard drives. I think if you look at CD-ROMs, they're called AT devices, advanced technology, I think is what it stands for. I think they use 4096 sectors. But think about when CD-ROMs came out, they're much newer. So the idea of 512 bytes maybe was completely appropriate when hard drives were first a thing. But when we started using CDs, now it's like, oh, well, maybe that's not big enough anymore. Let's approach this differently, even though it's, you know, we're kind of the same idea is working here. We're working with a magnetic, well, actually, CD-ROMs are not a magnetic medium. Floppies were magnetic mediums. CD-ROMs were actually it read the depth differences. So they called it burning a CD or whatever, but it was actually creating like a track where you can read on and off based on the depth of whether something was burned or not burned. It's like a divot. Okay, so we have this idea of a file system. Let's finish drawing our picture here. So file system says we have a bunch of blocks. So we're going to draw our blocks here, and blocks, of course, are pink. Actually, I'll probably have to make them a couple different colors. I'm going to make our blocks relatively small here. So this is block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 7, block 8, and I don't know how to count, block 9. I'm stopping at 9 because I don't think this guy will hold the 2-digit value. So this is a really useless hard drive. Okay, so we have what 5,120 bytes of data that this hard drive has a capacity for.
Yes.
Use your
The most optimized hard drive.
Use your storage wisely. All right, so these are our blocks. I'll label this out here. Okay, these are our blocks. Now, these blocks, remember, are abstractions for our sectors. I have to shrink down the text here, but this is 0.511. I can't shrink the text on this guy. Text. Nailed it. All right. 0 to 511. This guy is 512. Oh, he's not going to be big enough. 512 dot 1023. This guy is 1024 dot 1024 plus 512. Ooh, plus 1535. This guy is 1536. Dot plus 512, 2047. This guy is 2048. Dot plus 512, 2559. This guy is 2560. Dot plus 512, 3072. 3071. $3072. Dot plus 512. 3583. 3584. Dot plus 512. 4095. 4096. Dot plus 512. 4607. 4608. Dot plus 512. 5119. These are our bytes. And these guys here are our sectors. Let's actually say, do it like this. Sectors 512 byte in size. And I would change the color here, but I think that also will shift my font. So if I make this a different color, like I make it white, yeah, it switches my font. So I can undo that. So blocks and sectors are closely related in terms of the color I use. All right, so we abstract blocks by saying this is block 0, block 1, block 2, and those guys they encapsulate a bunch of well, actually, I still have this misrepresented. So so one block in our modern language we decided is 4 kilobytes of sectors, right? Which means I need 8 sectors. 1, 2, 3, 4, 5, 6, 7, 8. So these sectors are actually what is governed by this block. So block 0 is an abstraction for those 8 sectors. Block 1 would be an abstraction for these 8 sectors, pretending like the text is readable and correct. So assume I changed my bytes in here to continue on from where this guy lives. So this would be 4096, blah, 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 blah. So just so it's, I'll just put dots in here. I think you get the point of how I counted. I counted by 512 bytes. So this is the first 512 bytes. This is the second 512 bytes. This is the third 512 bytes. First sector, second sector, third sector, fourth sector, fifth sector, sixth sector, seventh sector, eighth sector, ninth sector, 10th sector, 11th sector, so on and so forth. So if you wanted me to number those. This is sector 0, sector 1, sector 2, sector 3, sector 4, sector 5, sector 6, sector 7, sector 8, sector 9, sector 10, sector 11, sector 12, sector 13, sector 14, sector 15. So I've depicted the first 2 blocks here as governing as being an abstraction above these 16 sectors. Because each block is a collection of 8 sectors in contiguous memory. These sectors are right next to each other. These sectors are right next to each other. The sectors associated with block 2 would be right next to each other. Block 0, block 1, block 2, these guys are contiguous in memory because their sectors linked directly to each other, right? But a file does not necessarily get stored contiguously. I could store a file in block 2, 6, 5, and 3. In fact, I think that was from the example in that video, right? The beginning of the file was stored in block 2. The second block of that file was actually in block 6. The third block of that file I thought was block 5, but whatever. And the fourth block was in block 3. So notice that file is not stored in contiguous memory. The file is stored in 4 separate blocks, and those blocks are linked to each other by the file allocation table. Okay? So physical hardware, operating system abstraction of that physical hardware, saying blocks are collections of sectors, then a file system that says, how am I going to keep track of these blocks? I'm going to keep track of those blocks using a file allocation table. So this guy will manage all these. Put a little vertical line in between these, letting you see that there's a separation. Okay. Then I can drop all this down. All right, so the file allocation table is what manages these blocks. I'm actually going to write it over here. Manages the links between blocks or how files are stored. And then we have directory format table, which manages the first block of each file. So this guy knows about the head of all the linked lists. This guy knows about all the links between the blocks in the linked list. Because even though we're conceiving of this as a linked list, it's not our linked list that we've written before, where we actually have instances of objects that have next node pointers. In this case, the next node pointer is a place in our file allocation table that tells us which block to go to next. And then we run to that block because we can get to that block by just zipping to a certain number of sectors. So if I say, how do we traverse a hard drive? Well, we know this is a collection of sectors. And 512 byte divisions. So if I need to get to sector 8, I will take 8 512 byte steps to get there, where a step involves the hard drive spinning and the read-write head changing its position on the magnetic disk. So that's the mechanical portions of the hard drive, right? This hard drive is a spinny disk thingy, and we say, read write head, go to sector 8. And he'll spin and go to sector 8. And that's called seek time, right? Hard drives have different speeds, and the things that drives the speed is what the RPMs of the hard drive, right? It's spinning faster, so it can read write faster, whatever. But that creates then more heat, and you need to deal with data destruction and things like that. How do you cool it and all that jazz? So you kind of seeing the levels of abstraction we're dealing with here. We're talking about a physical hard drive in terms of how he works. And then we're talking about how we choose to interface with it, right? So this is my, I don't know if you see my can, this is my soda can. So here's the physical hard drive. What's inside of here, all the chemicals and things like that, I don't have any control over. That was dictated to me by, who is this, Coca-Cola? Sprite Coca-Cola, or was it Pepsi? Coca-Cola. So Coca-Cola came up with the formula for whatever Sprite is. I interface with this guy by opening this tab, right? And then I drink the liquid. And that guy, so the tab, this little hole is the interface. And then how my body processes that is also, that's out of control of Coca-Cola, right? So these are two separate systems interfacing with each other through this conduit. So in our case here, by this picture, we have a system that is a physical hard drive. That's my Sprite can. And then we have this operating system, specifically his file system, which connects to this. So in our example here, so my Sprite can, the hole in my Sprite can, which is the conduit by which I'm able to connect to the Sprite can, what's the equivalent to the hole in our Sprite can in this picture? If the hard drive is our Sprite can, and the operating system is the human, what's the equivalent of the hole in our Sprite can? Probably this guy right here, our blocks. So we've decided that our interface to these physical sectors is through blocks. Okay? If we want to just keep going, we can say, well, that's how the makers of Seagate or Western Digital have designed their hard drives. But technically, they put the hard drives together in terms of atoms. And then you have subatomic particles and how they work, the nuclei. And so, I mean, we could keep breaking it down until we get to, just this, subatomic particles and how they interact with each other. So everything that we're talking about here is an abstraction of the level beneath it, right? Human beings are made up of a whole bunch of atoms, and those atoms are thought to be made up of a whole bunch of other things. And then you might have subatomic particles, where you have the particles that make up atoms might be made up of a whole bunch of other things. And then you get into an infinite loop, and that's where God exists. So I think we just proved God right here. So check mark, Christian worldview. So, in any case, the everything is an abstraction of something else. And when we think about abstraction, if you go back to your 150 class with Dr. Locklear, he had a slide on there called, on the abstraction slide, and abstraction means simplification, right? It probably had a little picture of, I think he uses Einstein on his slide, right? So what are we doing here? Well, we're going from sectors to blocks. So we are simplifying the idea of sectors into blocks. We're abstracting them because it's more convenient for us to deal with our chunks of our hard drive in terms of blocks, because the way we're going to store stuff is likely going to be closer to in block-sized chunks than in sector-sized chunks. Then we have an abstraction. What's the abstraction of a block? When something blocks, when we have things that get blocked, what is the thing that we block and unblock? That's our file. Files are blocked into 4 kilobyte blocks to be stored, well, to be managed by the file system and ultimately stored on the physical sectors of the hard drive. In our example here, 8 sectors per block. So when we store a file, is blocked into 4 kilobyte blocks to be managed by the file system and ultimately stored on the physical sectors of the hard drive. When we retrieve, we'll call this story file on hard drive, retrieve a file from the hard drive and load it into system memory. When we open a file from the hard drive, we're putting it into system memory. So when we retrieve a file from the hard drive, we unblock the file into its bytes. So this like merges the sectors from the potentially multiple blocks together into a single file. Then, since we want it in system memory, we must interface with the OS's memory manager. And in this case, since modern day memory managers are typically paging memory management, so which might follow a paging memory management model, we have to divide up our bytes into pages and ultimately store them in the frames in physical memory. And if we want to fully have this slide complete, typically when we're storing something, we're storing it from physical memory into the hard drive. So we're storing a file from memory onto the hard drive. So we first need to marshal the stuff out of physical memory, because in physical memory, it's currently stored in pages, right? So we marshal that's a CS term, bring all the bytes together, okay? There, we'll leave them. Bring the bytes together by reassembling the pages in memory associated with this file. Then divide the bytes, call this blocking. We block the bytes into 4 kilobyte blocks to be managed by the file system and ultimately stored on the physical sectors of the hard drive. You see the abstractions working in both directions? So if this is, we're just looking at one little angle of our computer. And in this case, we only have a picture of half of this slide. We have a picture of how do we If we already have a file in bytes, so we didn't even do this step. How do I divide it and put it on the actual hard drive? That's the piece that we have in that picture. We have our bytes, which we ultimately are going to store in sectors. We abstract them in terms of blocks, which are dictated by our file system, which the operating system uses to interface with the hard drive. Somewhere out over here, we might have our system memory, which would then have a memory manager that we use the paging model to interface with system memory. And in between, we might have a file that came out of system memory, goes through the operating system to get stored in the file system. Or you might have a file that came out of the file system, goes through the operating system to get stored into memory. All right, that makes sense? So easy, trivial stuff, no big deal?
I have a quick question.
Nope.
Come on.
What's up?
So when you say paging, so for example, if you gather all of the information, and then when you say paging, so then we having like, for example, 4-byte resolution, so it would chop into like 4-byte chunks?
Depends on what paging memory management model you use, yes. When I'm talking about paging, I'm talking about this black box that's sitting over here. So we have our memory manager. This guy manages our system memory. And so maybe a paging memory management model. However, this is implemented in this operating system. Right now, we're focused on the file system portion of this. But this guy, this operating system has many features. He has a file system. He has a memory manager. He has a process scheduler for the CPU. So these are two of the moving parts of our operating system. And sometimes we take things from the file system and put it into memory. Sometimes we take stuff from memory and put it into the file system. And we do that by connecting these two things together. And who connects that phone call? It's the operating system. So you think back to the old telephones where you had the person who had to plug in the two wires. You know, the way back when. Where, you know, you pick up and it was like, operator, like, yeah, I want to call Wilma. And then Airwolf came out of a volcano. So the operating system here would connect those pieces to each other. So what I'm saying is in our discussion right now, memory management isn't something we're talking about right now. I've referenced it in the last week or so when we've been talking about how does memory typically work. This is a topic that should have been covered in 350. You should have talked, I think you guys told me you did talk about paging memory management in 350. So otherwise you can go and look up how paging memory management might be implemented. It's unimportant to us in here, other than the fact that somehow this memory manager will divide up a file and load it into buckets of memory. And a modern day approach to that is through something called paging memory management, where it divides it up very similar to here. Instead of blocks, they're called pages, and they're a lot smaller in size. So a block is 4K, where a page might be 4 bytes, for example. You would have much smaller pages because of the nature of how memory works, and we have a lot smaller memory total amount than we have buckets of a hard drive. All right, but this guy works somehow. That's not our concern right now. We just know that when we're dealing with our file system, we move things in and out in terms of blocks, which are abstractions for sectors. And ultimately, those guys get over here into main memory, because typically the go-to move in an operating system is files are stored in memory, and if we want to store it, memory is short-term. So I create a slide around this. Types of memory. This is something we talked about kind of last week, right? So system memory, I think we call that volatile memory, is for short-term, relatively fast access. Hard drive, non-volatile memory, is for long-term, relatively slow access. Typically, we move things from hard drive to memory. Let's call it system memory. Or from system memory to a hard drive. That's one go-to move we have. Or we move from a hardware register to system memory, or from system memory to a hardware register. So this is called a load instruction in assembly. This is called a store instruction in assembly. So this is the move from back and forth between system memory and the hard drive. This is the move back and forth from system memory and the processor. So if I want to get something from the processor to the hard drive, I go by way of system memory. And the operating system handles those connections for me. So that's something we've already seen in our operating system implementation. And we just might as well make this slide look real impressive. This guy, now we have our CPU manager. And he has his registers. And we'll throw cache in here as well. Okay, so there exists a road that goes from CPU manager to system memory, but we can't actually get from CPU directly to file system. We can only get from CPU to file system by way of memory. So we have to go from here to here, then we can get over here to the file system. So we're only putting stuff over here that we want to last long term. What dictates how do we store stuff long term? Why is this guy, this whole plan over here, why is it meant for non-volatile long-term memory? Or how do we make it work for long-term memory as opposed to this guy who only works for short-term stuff while electricity's flowing? Why didn't we have the equivalent of a file allocation table for memory management? Because we don't, right? The allocation table for paging memory management is loaded into system memory. This kind of goes back to something we dealt with early on the semester where we just said, let's kind of reserve the first, what did we say, like, was it 1 megabyte? 1 megabyte of RAM for stuff. We're gonna put stuff inside of our first 1 megabyte of system memory, and yeah, we'll put stuff there. And because we have stuff there, maybe something that we have there manages where the pages in memory are, right? But if system memory, this guy right here, is by nature volatile, which means as soon as we stop flowing electricity through it, it forgets everything that's in there. Having that stored in system memory, that equivalent of the file allocation table in system memory means that we will not remember it through boots of our computer, right? Memory gets wiped. You know, if you have a laptop today and you shut the lid to your laptop, it kind of powers down, right? It does what called hibernate. What do you think happens when a laptop hibernates? Go ahead, Blaine.
Keeps electricity flowing through the system. It'll just power down the screen, basically, is my guess.
Wouldn't that be terrible for your battery life?
Well, okay, fine. So maybe it stores what's in memory into the hard drive.
Yeah, it probably does that. Okay. Yeah, so unless you disable that, right? You know, because you can go into your power settings and decide, well, if on battery power, what happens when I shut the lid? Do you hibernate or do you turn the screen off? You know, so you don't burn out your screen, but it's still technically on. Usually if we're hibernating, we expect, you know, if you have 90% battery life right now and you shut the lid and you go about your day or whatever, and you get to your next class 2 hours later, if you don't still have 90%, you expect to have like 86%, 87%. You expect to have most of that battery life, right? You expected that your machine was not sitting there running for the last 3 hours. So what has to happen in order for it to remember the current state of memory? It has to copy that over to the hard drive. It's effectively the same thing as a context switch when we go from the CPU to memory and back to our stack and back. We're seeing the same patterns repeated over and over and over again. We're just calling them by different names, right? Go ahead, Blaine.
Do we have a name for our context switch between memory and storage?
Hibernate.
Okay.
there might be an official term. I don't know what it is. I mean, it didn't exist before we decided, hey, sometimes we are going to shut the screen of our computer down, and we want that to have meaning and save battery life. It's something that's much newer because of mobile computing. Yeah. So in any case, that's what's happening. It's copying the information from your memory manager out of your out of here into a place on your hard drive. Usually there's an area called swap space, or it's called virtual memory, whatever. Fake memory made of hard drive that is by definition non-volatile, so it'll survive power outages, that type of thing. It's going to copy it over there so that when you lift your laptop screen, it's going to have to copy that back in the system memory to pick up where it left off. Which means, like, for instance, my computer here has 64 gigs of RAM. So if for some reason I'm like doing crazy stuff on my laptop, and I bet you I probably am using a lot of my memory right now because I have Ubuntu up and things like that. So I say a lot. I'm probably using something like 16 or 20 gigs of RAM right now between having all my VMs open. But, you know, let's just on a ridiculous, like, let's say I have a whole bunch of virtual machines open and I'm purposely trying to use my 64 gigs of RAM. At that point in time, when I shut my lid, it has to copy 64 gigs of crap from my system memory to my hard drive, along with the allocation table for that system memory, in order for it to hibernate. Similarly, when I open the laptop lid, it's got to bring that back from the hard drive into RAM to recover from where I left off. That's going to take time. So usually we're not using that much stuff. And usually there might be aspects of things that are in memory that are considered kind of flagged as temporary, not necessarily required to be in memory when we come back. So there might be a difference between active memory, where we have something called a dirty bit. If you remember from 350, you talked about paging memory management. You can kind of mark whether a page has been recently accessed or hasn't been recently accessed. So there's different approaches to optimizing those systems, let's say. But that isn't the point of this class. Typically in this class, what we're looking at is, you know, if I was an OS writer back in the 80s, what decisions might I have done? This is the applied side of it. So while looking at a paging memory management used following a very modern model would be interesting, we would probably agree that whatever memory management they're using in modern day operating systems are probably significantly more complex than the memory managers they used in operating systems in 1990. Is that a fair statement? Because we were dealing with bigger numbers, faster things, bigger expectations, whatever. So in here, we don't necessarily want to focus on, I mean, we could have a whole class on paging memory management, modern day implementations of paging memory management. What we want to look at in here is, give me the, you know, if 350 is the high level picture of what is paging memory management, in here we might say, okay, if I was forced to write a memory manager, what might it look like? And we did. We wrote a pretty ghetto memory manager, right? But it solved the problem we were trying to solve. So we put ourselves in the shoes of somebody from the 90s or the 80s who was saying, I have this much memory to work with. I need to come up with some sort of mechanism for keeping track of it. We wrote that. We put ourselves in the kind of the early day pioneers of computing. We're going to do the same thing here. You know, we're going to be looking at kind of a very older approach to a file allocation table. We're going to see that it's very close to what we're doing today. We're only just now starting to push the limits of it because our hard drives are getting so big. And we've taken a little tiny step back now with our hard drive size, because now we've diverted from mechanical drives to solid state drives, right? So we gave up some capacity in exchange for speed. But now what's happening is the capacity is catching back up. It's like, well, you know, for a while there, we were at 2 terabyte hard drives, and all of a sudden we went down to 256 gigabyte hard drives or 128 gigabyte hard drives for all that extra speed. But now a 1 terabyte solid state drive is reasonably affordable. And it's not going to be that long before a 2 terabyte one is. And then before you know it, mechanical drives will just be dead. They're not going to be around anymore. You know, they got moving parts. They got, who needs them? You know, now you buy a gaming computer. What does it come with? It comes with a 2 terabyte mechanical drive, and it comes with a 32, 64, 128 gig solid state drive, like an M2 drive or something like that. So some super, super fast drive for the OS. And then who cares how slow it is drive for your game? Because once it's loaded into system memory, hard drive doesn't matter. The only reason you needed the drive is to boot into Windows quicker. You could have survived without that too. So, you know, it's that type of thing. Okay. So that's the context of what we're looking at here. So what we want to implement for our homework, and we're going to do this, so create this outside of our current OS with box. Just because of time, I don't want to complicate things by having to go through the box system, because I want to focus on more of the data structure things of this. So we are just going to implement a file manager in C that could be used by a OS. So in our little world, we would need to integrate it into our emulated OS if we really wanted to use it. But for now, we are just exploring the file system itself. All right, so we won't actually integrate this into our OS. So everything that we've been doing in our OS up to this point, you can just kind of put on hold. This is let's call this a separate project. Right? You don't need to worry about your box resource file or your emulator. You'll be able to test this by just running it from the command line. You have access to all of your stuff. You won't need make files and all that stuff. We're just focusing on what we've talked about today with our memory management. Okay, so we are going to create a programmatic representation for a hard drive that has sectors and a file manager that abstracts those sectors into blocks, which means we need a representation for blocks. Representation for a hard drive that has sector and file manager that abstracts those blocks, sectors into blocks, which means we need a representation for blocks. Then use, let's also say, create a data structure for a file allocation table, as well as a directory allocation table. You could say this can be simple, just needs to know the first block of each file. So the file allocation table is really where we're focusing. So then we're going to create, using all these tools, using all these data structures. At that point, we've just created a couple of structs and probably a file. We do some file IO and C, something like that. So I mean, this seems like a lot of stuff here, but we just kind of got our Legos out. So we got a block, we got a hard drive Lego that has sectors in it. And what's a sector? Well, it's 512 bytes. That's just what it is. All right. So we're going to now create a simulation that allows the user to store a bunch of files of a given size onto on the hard drive and show the contents of the file allocation table as well as the directory table. We'll stop there. So you're only going one direction. Only going the direction of blocking the data, turning bytes into blocks, where a block is a collection of 8 512 byte sectors, as we talked about today. So if I was going to show you an example, your program might say this: how many bytes is your file? And let's say I put in that this guy is 25,000 bytes. All right, so 25,000 bytes divided by 512 is going to take up almost 49 sectors, right? So I should then get a file allocation table. All right, so I'm just going to kind of say this file will take 49 sectors. 49 divided by 8. This file will take, what was that, 7? 7 blocks. Then show the file allocation table. And show the starting block for this file. So it doesn't have to be a fully functional file system manager. It's just that first part of it. Take a file, split the file into sectors, further split it into blocks, then store those blocks somewhere. If you wanted, the cool kids might say, I'll randomly put it at various blocks in the hard drive, and as if there's other crap already on there. And then, but what I expect most of you to do is just have it contiguous blocks, but show that it's block 0, which links to block 1, block 1, which links to block 2, block 2, which links to block 3, but the linking of those is done in the file allocation table. All right. The one last thing that I'll put on a slide here, just in our, I know we're a minute over, but whatever, deal. How many of you have ever defragmented a hard drive? Okay, several of you probably, your computer pops up and says, your hard drive needs to be defragmented. Would you like to do that now? What does defragmenting a hard drive do?
Like rearrange. Doesn't it? It optimizes the paths, right?
I asked you. I don't think you're allowed to ask me. By the way, I'll give you a hint. The answer is in what we just spent the last 2 hours talking about. What does defragmenting do?
Doesn't it just like rearrange like where those sectors are so that they're like basically contiguous, so the drive doesn't have to keep bouncing back and forth to read like a single file?
We're halfway there. Sectors can't move though, right? Aren't sectors contiguous?
Oh yeah, the blocks, I mean.
Yeah, the blocks. So defragmenting says rearrange the blocks and update the file allocation table to get files closer together in terms of block storage, i.e. read-write head does not need to move as far to get to the next portion of the file. And this also opens a larger portion of the hard drive at the end, meaning that the current data stored on the hard drive is closer to the early sectors on the hard drive, which means data access will be faster. That's what defragmenting is. Exactly, it's the mechanical side of what we talked about today. I have this file allocation table that tells me where the crap is stored. I have the hard drive itself that actually stores the crap. And once through days and days and months and years of use, that stuff is a pretty good hodgepodge. Technically it works, but I got data stored all over the place in there, from files I've created, files I've deleted, all sorts of stuff. So now what I'm going to do is I'm just going to reorganize that and update my file allocation table to have a much more orderly file system, even though it's the identical data that was stored on there. And that's why defragmentation takes so long, because you have to rewrite that file allocation table. And you imagine how big our hard drives are today. All right, questions about what I'm asking you to do. You're going to want to sit down and spend some time thinking about how you're going to start writing this code before you just dive in and start writing code. It's not going to be that bad, even though it sounds scary. Make sure you understand what we've talked about today. You should have a very good understanding of this slide. We talked about a lot of stuff today, but this is important stuff. Cool? All right. Anyways, that's all I have for you. Like I said, for registration for the fall, I strongly encourage you to look at some of those new classes. I know some of you are graduating, but if you're not graduating, I strongly encourage you to look at some of those new classes. I also encourage you to start looking ahead at early start on the master's program while you're still an undergrad. Even if you aren't positive you want to do a master's, you know, you've already paid for the tuition. So if you have at least 3 credit hours of room in your schedule in either your fall or your spring of your senior year, you can squeeze in a grad class here and there. It won't help you in the undergrad, but you've already paid for the credit hours. So you might as well get a couple of grad courses under your belt for what you've already paid for. So in case you go and do a master's degree, you'll have to pay for that much less in case it's coming out of your pocket. Or if you're lucky like Blaine, your employer will pay for your master's degree. I assume you're doing a master's, Blaine? The answer is yes, by the way, just so you, in case there was a confusion in your head. All right, I will see everybody on Monday, but I'm around all week. So if anybody's in town and wants to come play with our new, we have a new 100-watt laser cutter that I almost burned down the makerspace with the other day. Because we're using it for cutting out the face shields for the clear plastic face shields for the 3D printed things that we're creating that go like headbands and the face shield comes off of it. And so it's this giant laser. I mean, the thing is huge. It's like the size of a, I don't know, a compact car or something like that. And so I assembled it because you could put like big sheets of stuff in there. I mean, you can cut wood, you can cut marble. I think you might be able to cut some very low melting point metals. So not like, it does everything but metal, I think is kind of the advertised thing. But I mean, you can cut thick things with it, but it can hold things. I think it's 40 inches wide, 30 inches deep. And then I think it's like 24 inches tall. So it could cut through something that is 2 feet tall. You got to crank the laser for that guy though. But so when we were installing it this weekend, we hooked up the the laser ships in a separate box. So you have the giant canister thing, and then you have the laser, and you got to marry these things together. And so you got this wire. So you got a red wire and a black wire on the laser, and a red wire and a black wire on the machine. You got to connect with each other. And the machine's red wire and black wire is a lot thicker than the laser's red wire and black wire. So at first we decided, oh, well, we can just strip these and kind of twist them together, just with your hands, just all ghetto style. And then we said, oh, well, we probably should put electrical tape around this, right? So we have electrical tape in the makerspace, but 3 feet from us was this like thing of tape that came with the laser that we thought, oh, this must be electrical tape because it kind of has like rubbery, it feels like that. It wasn't. It was tape made of paper that was actually meant to be flammable, in my defense. So, so we had this ghetto twisted laser wire attached to the thing that we then wrapped in flammable paper. So as you might imagine, the first test didn't go well. We had a fire and nobody got hurt. The laser survived. Then we realized, oh, we probably shouldn't have been using the paper, but maybe our twist is fine. So we kind of, tightened up our twist a little bit, went and got the real electrical tape, wrapped it around there, tried it again, got another fire. Okay, so apparently this whole ghetto twist thing is not the right way to doing it. So we went over to Home Depot because we were too lazy to solder it. So we went over to Home Depot and got the wire twisty nut things and put that on there, and then put the electrical tape, and then it worked. So we started cutting some stuff, but now it's still sparking. Maybe 20% of the time it sparks quite a bit. So yeah, I think we need to get a professional in there to wire this puppy upright. Is the the idea here. But hopefully they're coming tonight. Oh. In fact, he just messaged me, and I have to go meet him now. Perfect.
Cool.
So I will see everybody on, what day is today? Oh, Monday. I'll see you next Monday, but I'm around all week. Have a good one.